session. So let me start recording. All right. Hello, everybody. Welcome to the Statistical Foundation of Reinforcement Learning. So this is a PhD level course offered by UCSB Computer Science Department. My name is Yu-Xiang Wang. You can call me either Yu-Xiang or call me Professor Wang. So whatever you like. I prefer you call me by my first name, but Professor Wang is also fine. All right, so the course is going to be about reinforcement learning, and this is a smallish class, so I hope to make this as interactive as possible. If you are have questions, and yeah, feel free to type in the chat, and I can address them asynchronously, or you can maybe unmute yourself, or you can raise your hand, and then if you want to speak up. Yeah, just bear in mind that since the lectures are recorded, if you turn on your camera or unmute yourself to speak up, like you will be recorded in the lecture. So I do not currently plan to release the lectures publicly. So these recorded lecture are only going to be made available to those who are registered for the class, and those who are interested in these materials at a very small scale. So there shouldn't be any like issues about copyright. But bear in mind that if you unmute yourself and then you are recorded, and if your images shows up in the video, then I consider that you have agreed to made yourself and your participation in the course available to the rest of the class. Okay. Yeah, we now have 32 participants, so let's get the lecture started. So yeah, let me try. Hello. Good. So it looks like Apple Pencil is also working. So the course is going to be about reinforcement learning. So what is reinforcement learning? So RL is a particular algorithm in a particular setting in AI and machine learning that's getting increasingly like heavily researched on. And RL is a control theoretic problem that also intersects with learning. It is about an agent interacts with an unknown environment while learning what this environment is about, how this environment works, and how to choose a sequence of strategic actions in order to maximize your cumulative reward through the feedback of the environment, right? So this closed loop like speaks of the control component. Meanwhile, the unknown environment requires the agent to learn from stochastically observe the rewards and states, and the fact that you need to take actions to interact with this environment suggests that there's also an experiment design component in that you have to somehow choose your actions in ways that identify the interesting part of the environment that's useful for you to maximize the reward. Okay, so we'll have a lot of fun with this, but for now, let's take RL as a general framework of learning of how an agent interact with the environment I wanted to be successful. All right. So as I said, RL is among one of the hottest research areas in machine learning community right now. So last year, actually 2 years ago at Europe's 2019, there were more than 200 papers about reinforcement learning, both in theory and in the applications. And this year, there are even more, and we're seeing an exponential growth of research into reinforcement learning in the machine learning community. So it is a good time to hop on the rising trend, and then like working on. So you are lucky starting to work on reinforcement learning a year ago or 2 years ago, because then you'll get a lot of citations. Yeah, some of these applications involves playing games. So most people must have seen AlphaGo, right? So they shoot a movie out of this, a documentary. So the game of Go is an ancient game that has an astronomical number of states that that has long been sort of unsolvable by computer due to the exponential blow up of the number of states and search space. And on the other hand, like when people apply reinforcement learning type techniques and try to learn something in practice using learning-based methods with carefully chosen function classes, and then it becomes highly tractable. So currently, I don't think any human on Earth is able to beat AlphaGo or AlphaZero. That's just purely AI. So obviously, reinforcement learning has applications in robotics, and also this is a so-called bandit problem. Suppose you want to go to a casino and then maximize your profit from the casino, even if the casino is rigged, and then you wanted to learn like which one of these slot machines has a maximum payoff. So that's a special case of reinforcement learning as well. And this kind of so-called bandit algorithms are very typically used nowadays for say serving advertisement and for say clinical trials that we want to online minimize the regret that we have about the patients that we have tried to test the different treatments on. All right. So besides like the aforementioned applications and say in games and in other situations where you have access to a simulator, people also start to consider using reinforcement learning techniques to real life applications. Obviously, for robotics and self-driving car, there are additional considerations in RL that we need to design algorithms that are safe and robust. And for things like sustainable energy, for personalized medicine and so on. So it is sometimes like not ethical or even illegal to try out different stuffs, which reinforcement learning agents actually need to do in order to learn. So there are a lot of considerations on how we're going to be designing our algorithms so that they apply appropriately in these motivating applications. Okay, so now about this particular course, right? So this course is a graduate level, a PhD level reinforcement learning course with a heavy focus on the theoretical foundation. So if you're looking to learn algorithms, reinforcement learning algorithms such as so deep Q learning, actor critique, and other methods, and learn the model architecture, how to construct a neural network, and then set up the experiments to learn how to play the game of Go, then this is potentially not the right course for you. Meanwhile, if you would like to understand the underlying mathematics behind reinforcement learning and how people started from theory and equations and come up with these fancy algorithms that actually solve like leads to breakthroughs in artificial intelligence, then you will learn a lot from this course. But bear in mind that this course is on the graduate level, so you should be comfortable with long mathematical derivations and be able to articulate mathematics at a level that is sufficiently mature. Okay, so you will you will learn about the intuition behind RL algorithms in terms of how people came up with those ideas for stochastic approximation and function approximation, and how people resolve the corresponding issues in these approaches in designing RL algorithms. And we'll also learn how to prove the sample complexity bound. So this is about how quickly can an RL agent learn. Well, given say a limited number of interactions with the environment, or given say a fixed data set that's collected before, how large does this data set needs to be before we can learn an agent policy that's in some sense optimal. Okay, yeah. So the purpose of this course is to prepare graduate level students in starting research in reinforcement learning. So after taking this course, you should be able to know what are known theoretically and what are still open. and what are some good problems, good open problems that you can start to work on in order to make scientific contributions. Okay, so that's a basic flavor of this course. So it's theoretically driven. We do have examples and a lot of illustrations, and I try to make this course as accessible as possible. But it is a theory course, so if you are not comfortable with theory or you're not interested in theory and just want to learn about algorithms, then like maybe this is not the right course for you. Okay, so I'm going to be covering the model of reinforcement learning, the mathematical model under which reinforcement learning algorithms are being studied, called Markov decision processes, and then I'll talk about reinforcement learning algorithms including some of their design principles and the intuition behind them. The big part of the remainder of the class will be focused on the theoretical analysis on two family of RL settings. So online RL, in which case it is important to consider strategic exploration. So this is about how do you choose a sequence of actions so that you can you can explore and exploit and maximize your cumulative reward, while at the same time try to learn something about the environment so that it can benefit you in the future. Right, so it is a very interesting set of recent theoretical results, and then I'll talk about offline reinforcement learning, and also the focus will be on theory. So we'll talk about what can we do if we do not have access to the environment at all, but rather have a data set that's given. Okay, so towards the end of this course, I'll talk more about functional approximation, in particular general functional approximation. But throughout the chapter 1, 2, 3, 4 of this course, I will mostly focus on two settings. So the first setting is when the reinforcement learning is dealing with a finite Markov decision processes where you have discrete random variables and everything is finite. You are in the nicest setting. And occasionally, I'll also talk about the cases when you have a linear Markov decision processes, in which case certain interesting quantities of the model is parameterized by a linear function with respect to some unknown linear coefficients. Okay, so we don't really have a like formal textbook, but we'll be drawing very heavily from this recent monograph by Argavar Nanjiang, Shyam Kakade, and Ren Sun. So this book is freely available online, so you should go and download it. Especially the first three sections of the course will be based on materials in this textbook. Though like some of the coverage of these materials will be slightly different, and maybe there's slight notational differences, but in general, this is a very good. I think the best theoretical reinforcement learning textbook that's out there. Okay, and Sutton and Bartle, so this is the standard entry-level introduction to reinforcement learning. So if you don't know reinforcement learning at all, so I think this is a textbook to read at the beginning, and it doesn't go into the depths, the technical depths of algorithms and theory and how those algorithms works, but it is an excellent textbook for building intuitions about reinforcement learning and learning the related techniques such as dynamic programming. All right, so here are some of the prerequisites for you to be successful and for you to enjoy this course. So as a graduate level course, there isn't really anything that I require you to have taken because you guys all have very different background. But meanwhile, these are some of the anchor points that I expect you to know already. So you should have taken a linear algebra course and know how to mentally and mathematically manipulate matrices and vectors and argue about these quantities on the vector space at a level that you don't have to zoom down to every element. yeah, but yeah, once you try it a little bit, then you will learn. You realize that your knowledge in linear algebra will just get better and better over time. So we also need probability series statistics and actually a lot of that since this is a statistical foundation course. And in terms of computer science preparations, so you will be fine if you know just a basic basic data structure such as arrays and multidimensional arrays and so on, and being able to say count the number of operations that you need to you need to say compute matrix multiplications and matrix vector multiplications and so on, and that will be good enough. Right. So very critically, the course will be focused on mathematical proofs. So being able to follow the sequence of logical arguments and come up with mathematical proofs is important for you to do some of the homework questions. Right. So the coding requirement is relatively simple. So we will only have like I think 1 or 2 coding questions in the second homework. In the first and second homework, the first homework 0 is already out on the course website, so you can go and check it out. So that's a kind of a level of coding that is required. So the reason why we want you to also have a little bit of a coding component in the theoretical course is because I strongly believe that people learn better when you have implemented at least a version of the algorithm, and if you have gotten your hands dirty for at least once before you start to focus on purely mathematical pursuit. Right, it helps you to deepen your understanding in whether things works and how things works in practice. So it guides you through your taste and choices of the research problems that you that you spend your time to work on. Okay, so that's the motivation behind the coding component. And some of these advanced knowledge, so these are first of all not required, but if you have taken previous courses, say on statistical machine learning, have some experience with things like Hofstad's inequality, union bound, Bernstein's inequality, and these things, it will help you. And from the RL side, if you if you were previously a computer science major, so you will be familiar with dynamic programming and Bellman equations and so on. So these are going to be very helpful in this course as well. Moreover, some fundamentals in optimization theory say when we talk about maximization and the argument that achieves the maximum and the objective criteria that we are maximizing the corresponding constraints and which constraint imply a set feasible region that is larger and smaller. So these are some kind of arguments that's from the optimization theory that we'll be using from time to time. So having some advanced knowledge on optimization theory will be helpful too, right? So the bottom line is that if you have some doubts of whether you will be enjoying this course or whether you will be spending an indisproportional amount of time to work on the assignments in this course, then you should try homework 0. Right? If you are doing okay in homework 0, I think you will be successful in this course. And I think I think most people who like finish homework 0 relatively easily, like should really enjoy this course materials that I will be covering in this course. All right, so now let's get to the part that how am I going to be evaluating your performance in this course, right? So first of all, the background is that this is a graduate level course, so I don't typically fail people. Well, another thing is that most graduate students should know that the grades do not really matter. So your time and effort should focus on research and the kind of research projects that you work on. If you can learn something from this course and apply to your research problem, then that's perfect. So that is the reason why a big part of the evaluation of this course is on on the course project. So homework, so we'll have 4 homeworks, consist of 40% and another 40% for the project. The projects are group projects. So you can also do individual projects, but you can have like 3 people working together. And to make it very flexible for you, you can choose any of these basic level or advanced level or something that's related to your own research. So the basic level would really be to apply the knowledge that you learn in this class and start reading a scientific paper in the area of theoretical reinforcement learning, and somehow to try to replicate their proofs, right? So 1 paper is sufficient for 1 quarter. And then at the end of the quarter, we will have a couple of lectures where students in groups will present their findings in their project. Now, a little bit about the first 2, the lecture attendance and scribing. So lecture attendance is required. So I will have records on who attended the lecture from list of participants. Meanwhile, like if you cannot attend the lectures, or you have other reasons that you would prefer the asynchronous, like just watching the course video, then that's perfectly fine too. But you need to let me know. Just give me the reasons why you cannot attend. So the reason that I'd like to encourage you to attend is because this is it is always a better experience to be interactive. And in the mathematical derivation, if you are stuck, if you ask the question right there, and that helps not just you, but also your classmates. Okay, so finally about scribing. So I've provided a template of anyone who's scribing for us on the course website. So this is in LaTeX. So the reason why we need this is because this is the first time this course is being offered, and I'm creating like most of the materials as the course go forward. So sometimes I do not have a well-written set of notes in a document format, so you guys can refer back to. So I will make the presentation slides available, but a lot of the course will be derivations that happens on a piece of paper. And the annotated slides will be released, but at the end of the day, it's always better if one of you can take a deeper step at each particular lecture and then try to create a document that summarizes what we've talked about in that lectures in a format of say a theorem and a proof with every line of argument mathematically verified, right? So that would be a substantial a component of your training to understand the lecture and being able to reproduce what we covered in the lecture by just writing it down. Okay, let me tell you a little bit more about the projects. So in order to avoid the issue that you do all the last minute work for the project and push that towards the end of the quarter, so chances are you will have other projects and other commitments that's also packed around that time. So I propose that you guys should provide this intermediate checkpoint. Say so these intermediate evaluations will consist of a different percentage of the course. Say the proposal, you should submit the proposal, say within the next 2 to 3 weeks, and the midterm report is due around the mid quarter before we start the last section of the course. So all the dates, specific dates of when these milestones are due about the project are already provided on the course website. Okay, so you'll so the proposal, a good rule of thumb is like half a page to 1 page. So basically you describe what you're going to do and which paper you are reading and what is an extension that you're planning to do. And the midterm report is like a 2-page document which summarizes your progress and your team and I guess like and the contributions of each team and what you guys are proposing to do for the remainder of the time before the project presentation. And the final reports will be due after our last lecture. So this will be a slightly more well-written document where you put in all your efforts in explaining the proofs of a particular paper carefully, and discussing the new technical stuffs that you learned. And yeah, so I will be reading these final reports, and I'm really hoping to learn from you guys and your and your adventures in reading these state-of-the-art papers, right? So so I can only understand that and provide feedback to you, and maybe some of these will turn into publishable conference submissions towards the end of the quarter. But then it really requires you to write a nice final report, such that I'm able to provide necessary feedbacks and guidance subsequently. Okay, so we will be having a discussion forum on Piazza. So if you so Piazza recently switched to a contribution mode, so you will sometimes receive ads, but just either contribute or ignore that. We'll be using the Piazza for all announcement, and well, I'll share a list of project ideas on Piazza hopefully by the end of this week, so you can start finding teams and figuring out the scope of your course project. All right, so this is a tentative schedule as I talk about. So we'll start with Markov decision processes, talk about the intuition of RL algorithms, and then we'll spend big chunks of time discussing about strategic exploration and about the offline reinforcement learning, right? And at the end, we'll talk about the more general functional approximation beyond the linear case. At the moment, the last 4 lectures are dedicated to student presentations for you guys to show off your findings in the course project. Yeah, but just bear in mind that this schedule is tentative. As I said, I'm creating these materials as the course move forward. And there's really like a big chance that I calibrated the course wrongly, and sometimes I won't be able to finish one topic in one lecture, then I'll just continue in the subsequent lecture. So the specific dates and the specific lectures, the topic of each lecture, so this is just a rough estimate. Okay, so yeah, it only makes sense to revisit those materials if they are not understandable, rather than to rush it through. So you won't be able to follow the remainder of the course. All right, so I've finished the logistics part of the introduction of this course. So at this point, like, do you guys have any burning questions? Is everything clear, or should I clarify like some of the details on the evaluation, on the scope, on the motivation of why I am doing some of the things that I plan to do?
I have one question.
Go ahead.
There's a lecture with title called General Function Approximation. So all the lectures before that will be linear function approximations.
Yeah, so the lectures before that are going to be mostly in the tabular setting, where we have finite state and finite actions, or the linear setting, say in this case the linear MDP, that's tabular MDP. So these are finite case, and linear case would be the case when we do functional approximation, but we do linear functional approximation.
I see. Thank you.
All right. Any other questions?
Yeah, I have another question. Is that I have already seen the sign up sheet for subscribing. So we just sign up on that sheet.
Yeah. Just sign up there. So each is first come first serve, and then of course you guys can swap amongst yourself. I think it makes sense for more than one student to sign up. So if at the end of the day, like we don't have enough slots for people to contribute to scribing, so I'll just change the evaluation policy to make the scribing bonus points. Yeah, so it doesn't affect so I shouldn't be penalizing anybody because you're not scribing for the course.
Thanks.
All right. Okay, yeah, so maybe we should just move forward. Okay, so in the remainder time today, so I'm gonna start the overview of reinforcement learning by talking about the problem setups, give examples, and compare and contrast reinforcement learning to other machine learning settings, and maybe other related problems. I also briefly talk about the motivation behind offline reinforcement learning, which is, I think, at least 1/3 of the course. And then once I finish the like broad overview of reinforcement learning, so I'll zoom into the mathematical model of reinforcement learning called Markov decision processes. I'll focus on setting up the problem for you guys to understand the notations, and then hopefully, so I'll have time to finish 1 or 2 proofs of some like non-trivial facts about interesting facts about Markov decision processes. Okay, let's get it started. So again, you've seen this figure. So reinforcement learning is about agent interacting with an unknown world and trying to learn about the environment through the feedback while optimizing the decision policies to maximize the cumulative reward. Okay, so the key difference from control is that now we have the unknown environment, and the key difference from supervised learning is that now we have to take actions to collect data rather than the data is coming from some distributions that are unknown but fixed. So so slightly more notations. So these are so we're using this calligraphic letter to represent the state space, action space, and these capital letter ST and AT, that they are, yeah, it is clear from context, but these are typically random variables. So this means the random variable of the state at time t, the random actions, potentially random actions at time t taken by the agent. And this RT is a real valued scalar, which measures the immediate reward that you receive at that particular point. Right. So sometimes like you do not actually observe the states. So this is the case in partially observed Markov decision processes. And in practice, I argue that this is always the case when there's a difference between the space of observations and the space of the states. So in this case, we'll be using OT to denote the observations. Now, I guess what is a policy? So a policy is like generally speaking, a policy is how the agent is going to be making the decision, right? So it is a lookup table for you to substitute the entire trajectory of state action reward or observation action reward triplets until this point, and then you need to take this as an input. Yeah, so I think I forgot I forgot this observation O or S, or sometimes you do not have this, but in other cases you do. So basically the agent is how the policy is how the agent is going to be making the decision. And it is also something that we're optimizing over. Okay, and the goal of reinforcement learning is to maximize the cumulative reward. And since everything, a lot of things are stochastic in the reinforcement learning problem, say state transitions can be random, the environment, because the environment is random, and the reward can be random. So the objective function needs to be a fixed value, which we consider, we just add this expectation here. So the goal of reinforcement learning is to maximize the expected cumulative reward by finding in some sense the optimal policy by start. Okay, so I also left this remark that when the state is observable, then it suffices to consider this policy that depends only on the state. So I'm going to be trying to formalize this. I'll try to formalize this fact as a theorem rather than just as a statement, as a restriction to the setting. Hopefully, it will be clear by the end of the day why this is the case. Okay, then there are distinctions between the different reinforcement learning settings called episodic, finite horizon reinforcement learning, and the infinite horizon reinforcement learning. So let me explain that a little bit. So in the finite horizon reinforcement learning, we are in a situation where the data comes in episodes. So let's say that you are learning an agent to play Super Mario, right? And your agent is in control of the joystick to try to overcome all the hurdles and save the princess at the end of the day. And you can repeat this game again and again and again. And each time you use this agent to start this game again, it's the same game, but like it may have different realized random values. So in this case, this is episodic RL. It ends with finite time because after say 200 seconds, if you still haven't passed that that episode, then you are considered dead, right? It's game over, right? So there's a fixed horizon t, or yeah, I think in most of the part we'll be calling this variable h, this constant h to denote horizon. And then the natural criteria for measuring the success of an agent is a cumulative reward. The infinite horizon reinforcement learning is more like a kid growing up, right? So you have this agent growing up, knowing nothing at the beginning, and then you have to learn everything within the same trajectory. So you live only once. You can never really repeat what you have done and answer the what if question. So what if I didn't attend UCSB? What if I chose to learn learn piano rather than cello when I was a kid? What's going to happen to my future reward? So in this case, typically you only have like one trajectory, and then you make decisions and that's it. And in order to make it more tractable, so people typically consider the so-called discounted criteria with this gamma parameter between 0 and 1 to capture to capture the goal of the agent to not only maximize the reward that are in the indefinite future, but also try to be a little bit more myopic and focus on what's going to happen today and tomorrow comparing to 10 years from now, right? So there's an exponentially discounted reward that's captured here, which essentially makes it very similar to the finite horizon, but it's still different. Okay, so a couple of examples of how do we instantiate these state action observations and rewards into concrete problems. So in reinforcement learning for robotic control, the states are going to be the variables that govern the physical world. Location, speed, acceleration, the objects that you're interacting with, where is it, the angular velocity, and so on. So those are the states. So sometimes you can only observe your own states, but not what you are interacting with, and there are various things that you cannot actually capture with your sensors. So therefore, your observations is a limited snapshot of the states or some projections of those states. Say from camera images, from the angles that you measured on the inertial measurement unit. The actions of this robot would be the how you change the torques applied to each joint and to systematically achieve the goal of say cooking this egg on this pan. Okay, and then how do we reward this this robot for successfully cooking for us? Well, so the rewards might be whether the egg is tasty and whether it is too salty. It could be whether the robot didn't manage to damage itself along the way, and whether this robot is able to take this piece of fried egg and bring it and serve it on the dining table, right? So these are rewards that we construct and we design so that to guide the actions of this robot. And it's also applied in, say, inventory management. In this case, the states are the current inventory level, the customer demand, and maybe about your competitor's inventory. So this is another reason why sometimes you do not have all observations of the state, because typically you do not know what the future demand is. You only have some estimate of that. And also you do not really know the details of your competitor's inventory. And yeah, but clearly it is part of the how the underlying world works, right? And the actions are going to be how many of each item are going to be stocking before Christmas, and the reward naturally in this case for the business decision making would be the cumulative profit over that period that you are planning ahead. Okay, so there are also this is the third application, say in a personalized medicine domain. So I got this example from Nanjiang. Where also the state will be the diagnosis, the actual test that you run, and the actual physical condition of that individual patient, and the action that you take would be the treatment, a sequence of treatment plan that you give to you prescribe to that patient, and then to measure the reward, we can check how well this patient is recovering. And then a learning system would keep maximizing the reward and with respect to the criteria that the doctors specify, right? So the diagnosis, I argue, is also an observation, and the underlying states are more complicated. Okay, so I argue that based on these examples, reinforcement learning is about decision making. Is in some sense the most general artificial intelligence framework. Part of that is because it tries to solve a very challenging problem where you do not know the states and you do not know the implication of taking actions at each state, and which states you're going to be transitioning into and what kind of reward you're going to be collecting. And you also do not know what's going to happen in the future and whether your state is accurate description of the underlying world. So nothing really known. So we can often cast most like other machine learning settings that are simpler into special cases of reinforcement learning. For instance, say in contextual bandits. So this is about simplifying the fact that there are dynamics and state transitions. So let's say that the states are IID sampled from some. So IID stands for the independent identically distributed. So suppose they are IID sampled from some distribution, and all you have to worry about is to figure out the right action to take, in this case, in these contextual bandits. And when there are no states at all, you only have, say, 3 actions to choose from, then that becomes a simpler multi-arm bandit, which typically correspond to the simpler clinical trial setting. And when we assume both the state and action are IID sampled, and all we have to do is to predict the reward, then this becomes this reduces to supervised learning that we collect like state action and reward pairs, and all we want to do is to predict accurately on the distribution that you get these state and actions. On the other hand, reinforcement learning actually tries to control this distribution so that the high reward state is visited more often. So it's a in some sense a significantly more complex setting. And sometimes in a control theoretic world, when we already know how the underlying dynamics works, when we know the transition kernel, when we know, say, the linear dynamical systems governing your robot, then this becomes an inference problem or a control problem, and indeed some of the techniques reduce to dynamic programming and reduce to things like common filter type of methods. And lastly, when we only have dynamics but no rewards, so reinforcement learning reduces to things something called a Markov controlled processes, where I guess the task is to figure out the underlying dynamics through techniques like system identification. So this has something to do with experiment design. So what are the impulse responses you can inject into the system to see the responses, and use the kind of responses to optimally learn the underlying dynamics. So as an example, let's say that we are using reinforcement learning and in comparison to supervised learning in a task that, say, Netflix cares about, a movie recommendation. let's say Bob is a Netflix user and on the Netflix website, and they are describing Bob by his user profile. So this is described by a feature vector that captures information about all the previous movies that Bob has watched and provided ratings and maybe written reviews on the Netflix website, right? And once you collect all this information together, you can process this into, say, a feature vector in R to the D. So what supervised learning does is to jointly learn a model so that you can use, say, you can take Alice and take Alice's feature also in RD, and then to predict whether Alice or where the Bob is likely to click on this recommendation, aliens versus predators. So Alice might have never seen either alien or the predators. So Alice might not be interested in this movie at all. So which is likely to be described by this feature vector. So supervised learning is gonna be able to do predict accurately in this case. On the other hand, reinforcement learning aims at like not the prediction problem, but rather the control problem. So reinforcement learning is gonna try planning way ahead of time and consider, suppose now I recommend this movie to Bob, and then there's a chance that Bob can click on this and maybe watch this movie entirely. And there's a chance that after watching this, Bob might be might enjoy this kind of a movie in general, and then that will change the corresponding feature representation of Bob, right? And then in this case, can I learn a policy that systematically create this kind of curriculum for Bob to learn from the movies, that I'll first recommend aliens, I'll then recommend predators, and both of them are highly rated. So maybe Bob, without seeing anything like this before, will likely to be interested in watching them. But once Bob have watched them and Bob discovered a taste in adventures and in sci-fi movies, and will then maybe the next time I recommend aliens versus predators, that will allow Bob to enjoy it a lot more, and then receive a more positive user experience, right? So the objectives that reinforcement learning is optimizing is more on the meta level. It is trying to optimize, say, user experience or maximize the bottom line of this company, or something that are not directly related to the predictions of the particular instances true. And that is really because when you come up with these recommendations, I argue this is the right model for this problem, because when you come up with these recommendations, you're actually changing your users' behaviors implicitly. So not modeling this fact will result in things that are suboptimal or not capturing the essence of the problem itself. Okay, so I hope this example illustrates the differences between reinforcement learning and supervised learning. And yeah, like we said, reinforcement learning is very general, but like with great power, it comes with great challenges as well. So this is a strong setting, therefore it is also very, very challenging. We have to learn a lot of things from scratch by trials and error, right? So we need to learn the dynamics, learn the reward function, and also learn how to come up with a good policy, and how to do planning, how to search the state space. So the plan of this course is for us to unravel these multitude of complexity into individual components, so that we can, say on the simplified model, understand each component independently. For instance, the beginning of the lectures, which is something that we will be talking about in depth today, on Markov decision processes. So in this case, we're fixing the dynamics. So the dynamics are known and there's no need to learn, and we're only solving the inference problem of how do we figure out what the optimal policy is for this underlying dynamics. So it is planning only. And then after that, we'll move on to reinforcement learning, but instead of jumping right into the full-fledged reinforcement learning algorithm, we'll study reinforcement learning. We'll study like something that's in between MDP and full RL, right? So in this case, we can sample transitions arbitrarily. So in some sense, we're assuming some stochastic data is already given to us, or we have some access to some samples from state transitions, and how do we learn from that? And this is where we can talk about the algorithm design and ideas without necessarily worrying about the issue related to exploration. And then, like, once we understand the algorithms, we'll move on to check what are the procedures and additional techniques that we can attach to this our algorithm so that we can explore the state space while not suffering significantly from exploration, right? So these are a very set of and then we'll also simplify this from the simple bandit problem before we move on to the full reinforcement learning under the Markov decision process. Okay. And well, so this slide is about the motivation of offline reinforcement learning. So from this example that we gave previously about the personalized medicine, so sometimes we cannot have access to the online trials and errors. We cannot just treat this cancer patient with a random drug just to try whether it will work or not, right? So it just doesn't work that way. So which means that the standard online reinforcement learning, where the agent has access to take actions and then receive feedback in terms of state and reward, say update and reward, it's not going to work in these situations. So offline reinforcement learning is precisely there to tackle these issues. Let's say that you have gotten a large logged data set, say from human doctors' treatment of these patients, and you've logged the patient's demographics and in the longitudinal trajectory and the different test results in response to different treatment. And so you've logged everything. So sometimes this log data might even be randomized. And then, well, the question of offline reinforcement learning is how do we just directly draw from this already collected information for the agent to learn a better policy to treat this patient? Okay, so that's the second half of this course is going to be about. So we'll start by formulating more concretely this setting of Markov decision processes mathematically. So specifically, we'll be dealing, from here onwards, there will be mostly drawing on the board, drawing on the slides, and the annotated slides will be shared on the course website after the lecture. So we'll start by talking about what is Markov decision processes and what are the parameters. So specifically, a Markov decision process is something where we have a tuple of parameterizations. There's a state space, there's an action space, there's a transition kernel, there's a reward function, and then a gamma discounting parameter. So this is between 0 and 1, and then the initial state distribution, right? So it is a tuple of 6 different things. So also there are various versions of Markov decision processes. So for this lecture and for many of the subsequent lecture, we'll be focusing on the infinite horizon discounted setting. So now let me parse even more some of what some of these things are that I didn't talk about at the beginning. Okay, so I'll start with P. So P is a transition kernel that is a function that goes from state and action pair to a probability distribution that is defined on the state on space, right? So you can also think about this as a conditional distribution of the next state given your current state and action. All right. So now this is called transition kernel, or transition probability, or just conditional probability distributions. And now the reward function. Reward function R is a mapping from state to action, to a real value. So for simplicity, let's consider the bounded domain. So the reward, the expected, right? Expected reward, expected reward function. So this denotes the expected value of the reward of time t given st is equal to s and at is equal to a. right? So this is defined as R of S8. All right, well, now I guess the remaining thing to talk about is this mu, right? So this mu zero is a probability distribution on S. So I'm using this delta to denote the probability simplex, right? So this is a probability distribution supported on this on this space S. Right? So basically, this is a distribution that the initial state is sampled from. So it may well be the case that the initial state is just it's just fixed, right? So you always start from the same location in Super Mario. Then it could be the case that then in this case will be abuse notation and then replace this nu with S, I guess with S0. Okay, so what else? So what is a policy? So policy is a mapping from the entire trajectory to an action. So the entire trajectory. So this is a union over all t from 0 to I guess empty set union with t from 1 to positive infinity, as st at are S1 A1 R1 to st at RT, right? And t minus 1 minus 1. Yeah, you do not actually observe the action and reward, but then when you make decisions at time t, when you make decisions at time t, so you need to depend on state variables st. So for now, like we won't be worrying about the distinction between state and observations as we talked about earlier. So let's say that we can actually observe the state, and we observe the state before we make the decision about which action to choose, right? Then this policy is fully general. It is everything, the entire history of the trajectories that you have observed so far, and then you can use those information to get a particular actions. Now, like, how do we evaluate any given policy, right? So let's say that this policy that I'll just drop this t, so that this actually means the collection of pi 1 to pi k and all the way to the infinite long Markov decision processes policy, right? So how do we evaluate individual policy, right? So the value of this policy, which will
so sorry, can I ask a
ahead.
question?
Yes.
So I'm a little bit confused about the writing for this phi u union t from 1 to infinity.
What
does
this,
that phi u
I see.
means?
This is not phi u. This is empty set. This is empty set.
Oh, okay.
Yeah. So this is empty set, and then everything else is a trajectory of a different length.
I see.
Okay, so again, this H denotes the history or the trajectories of unspecified lengths. Okay, so then let's specify this the value of a policy. So we define this value of policy pi to be the expected value when all the actions are taken according to this policy throughout, and when the initial distribution is S1 is drawn from mu, and then I sum over I guess 1 to infinity gamma t minus 1 RT. Okay, so this is by definition the exponentially discounted cumulative reward, right? So the first reward is not discounted starting from the second one on. The second step is discounted by a factor of gamma. The third step is discounted by a factor of gamma square, and so on and so forth until the very end. So clearly, so since we assume that this R expected reward function is bounded, And under like weak regularity condition, we can exchange the order of this expectation and summation. So that this is the same as gamma t minus 1 expected value of RT, expected value of RT. And since the expected value of RT is equal to R of ST and AT, right? It is bounded from 0 and R max, right? Therefore, we know that this expected this value of this policy is always, by geometric theory, is always smaller than R max over 1 minus gamma. Okay, so there's one more thing to define here, which is the so-called value function. So I'm using the capital letter V rather than the lowercase letter v to denote this. Yeah, so sorry, there should be an index of little, yeah, it's actually okay. So the value of this, the value function of this policy pi is defined to be the expected value when the initial state is equal to S, and everything else you follow you follow this policy, and this is the expected discounted cumulative reward that you will get in the end, right? So is everything clear? Yeah, so these two, in order to unify the notation, I'm also calling this v of pi to be v pi by just plugging in this mu into this place of S, right? So notice that this is a slight abuse of notation, but I just want to maybe avoid the clutter and avoid like small letter and capital letter representing different things. Okay.
I have a question.
Yes.
Does mu dictate what will be the initial state?
Oh yeah. That's right. Mu is mu 0. Yeah, sorry, that was on me. So mu is mu 0. It's specified here. It's the initial state distribution.
Okay, thank you.
Yeah, excellent question. Yeah, so I've defined the reward and the value function. So this is just a summary of what I just talked about. So notice that this is slightly more general because the immediate reward can depend on the state that you transition into. Yeah, this isn't just another equivalent representation that was preferred in a context when I prepared this set of slides initially. But I guess for the purpose of this course, so we can just ignore this dependence on S prime and then only consider this expected reward to be a function of S and A. Right, so it doesn't make much of a difference. So maybe I'll add a homework question to clarify this point. Okay, so we have the expected reward, and whenever we have an index, we have a superscript with a policy pi here. It means that the actions are taken according to that policy. So this is a consistent notation that's used in expected reward and also in expected cumulative reward, also known as the value function, starting from S. And now there's this value function called Q value function, which is closely related to the V value function. This says that you are currently at state S and you are taking action A, and subsequently you are following the policy pi, right? And then what's gonna then this is a cumulative reward that you get. So your initial state is S, and you take action A, and then you follow the first principle to construct this discounted cumulative sum, and then take expectation. Okay, also I hope these quantities are valid definitions to quantify like what the value of a policy look like. So let me illustrate this with a simple example called a grid world. So let's say that this is a frozen lake, and then your agent starts here, and this agent needs to somehow like overcome this barrier. So this is what you cannot step upon, but then move along the grids by transition into like one of the two states. So maybe this is a hole. If you step on this, you will fall into the lake. And this is like maybe the goal. This is maybe the bank of the lake that you'll eventually be safe, or some reward, some treasure chest that this agent wants to find. The issue is that this lake is frozen and it's very slippery. So the agent might have the intention, say, to go up, right? And then there's a chance that you won't end up being at this grid that's above you. Instead, let's say that the state transition probabilities, so these will be this P will be described by 80% moving up when you take this as action equals to up. We'll move up with 80%, and 10% you go to the left or go to the right, right? And if you bump into a wall, you stay where you are rather than moving anywhere. Okay, and we can also define the reward function. So these numbers denote this is reward function, reward S of A. And yeah, in this case, it's actually SA and S prime. And in addition to this, maybe the lake is very cold and the agent doesn't really enjoy hanging out on the lake. So you receive a slight negative reward for every step, which says that you should go as quickly as possible to the state here or here, so that you can end your torment on the lake. Okay, so this example is actually neither a finite horizon nor infinite horizon problem. It is, yeah, I guess discounted problem. It is an infinite horizon, but it is not discounted. And in some sense, it has like a stopping condition. So whenever the stopping condition is met, then the game stops. You can always convert this kind of MDPs into an infinite horizon problem by adding an absorbing state, which once you hit this game ender, then you switch to that absorbing state, and the absorbing state will always transition to itself and then give 0 reward afterwards, right? So this is one way that you can convert this problem into an infinite horizon problem that we talk about. If we think about this problem, what is a good policy? Like, should we go right or should we go up first, right? So it really depends on the different parameters of this setup. Let's say that this agent can take this pass, there, but you do not necessarily will move here if you decide to do this. So maybe you will go here. So these arrows on every grid would indicate the corresponding policy of that this agent takes. Yeah, and then we can evaluate each policy based on the specified reward and transition probability and calculate everything using the formula that we specified earlier. Okay, so there are other representations of the Markov decision processes. Say it's like it's intuitive to also represent it as a probabilistic graphical models. And for those who are familiar with this is straightforward. So these random variables are connected in this way with arrows pointing from one to the next, representing the dependence of the variable, and representing the causal relationships of these variables. You start from the initial state, and then these clique, I guess this clique would give you the transition dynamics, and the reward distribution is given by say this, right, by this clique. So the parameterization of the MDP models are really just the certain factorization of the joint distribution of these random variables. So sometimes you also see this so-called state space diagram representation of a Markov decision process. This is just a graphical representation of an alternative graphical representation of the states and its transitions rather than representing the distribution of the random variables. So in this case, you have 3 states and 2 actions, and these arrows talks about with certain probabilities, say you're at state S2, you take action A1 with 0.7%, 0.7 probability and 0.3 probability, you transition to S1 or stay where you are. right? And then you can specify the corresponding rewards accordingly using a separate function on the side. So sometimes having this graphical representation helps you to understand how this MDP problem works. All right. So we talk about how do we evaluate a particular given policy B pi according to the first principle. So expected value of the cumulative reward. So how do we talk about optimality? Yeah. So this is actually an interesting thing to address carefully, right? So we can define the optimal policy. I guess the goal, the objective of MDP planning is to find a policy pi star such that the V pi star of S is equal to the max of V for all S at the same time. Yeah, so I highlight this part that the requirement for optimality is stronger than just finding a particular policy that applies to like a given MDP with a fixed initial state or a fixed initial state distribution. Yeah, which always exists, but this is required us to find a policy that simultaneously maximizes the entire value function coordinate-wise. It is not a priori clear that this is even possible, right? So why would it necessarily why is it necessary the same policy that maximizes all coordinates of this value function? Okay, so MDP planning problem is to find such a pi star, and while sometimes we cannot hope to find the exact optimal policy, so the epsilon optimal policy, we say that the policy say pi is epsilon optimal if V of pi tilde of this vector is larger than V star minus epsilon, and this is like all one vector. Yeah, so when we talk about epsilon optimal policy, we want this policy to be optimal to be at most epsilon away from that of the optimal policy. Okay, so I hope this is clear. So it is unclear why such pi star exists, and so the first thing that we wanted to show is that yes, this exists, and second, we want to understand what does pi star look like. What is the kind of structure that this optimal policy may have? Okay, so we've talked about the general policy, which is defined to be a function that maps the arbitrary trajectory with an unspecified length to either an action or to a probability distribution defined on the action. Okay, so this is fully general. There's like two interesting subclasses of this policy, which seems to be restrictive, but we'll see that they're actually not. So the family of so-called stationary policy is all policies that uses only your current state. And the family of stationary and deterministic policy maps the state directly to an action itself rather than the probability distribution of. So you can see this is a family of all policy. This is a family of stationary policy. And even within the station policy, this is a family of stationary and deterministic policy. Okay, so we're gonna see that it suffices to consider the stationary policy, like in general, and well, also if we only care about finding the optimal policy, then there exists an optimal policy that's simultaneously stationary and deterministic. Okay, so these are actually like two somewhat surprising facts about Markov decision processes, and like very generally speaking, like we don't have to consider policies that are complicated in structure. Yeah, for instance, like the general policy can have various dependence in the past. It can have memory, and or well, it could be randomized. But yeah, so yeah, if we can throw away the memory and then consider only the stationary or so-called memoryless, then that's a benefit that we can leverage computationally and statistically. Okay, and the second fact is that, well, there exists a stationary deterministic policy that is simultaneously optimal for all initial state distributions. So this is something that's also worth thinking about why this is the case, because we are optimizing over a entire vector and we require pointwise optimality. Okay, so in the remainder time today, so let me hope to at least prove the first statement for you. So why does it suffice for us to consider only the stationary policies? So yeah, I guess I should remove deterministic.
I have a question.
Yes.
Will second hold for just fully observable MDPs and not for POMDPs?
Well, in my, like on top of my head, I don't know much about POMDP, so I don't know if I can understand your question accurately. But yeah, I can look up and try getting back to you.
Okay, no, by POMDP I just mean partially observable MDPs.
Yeah, I know. Yeah, I know. This course is not gonna be covering POMDP almost at all. So we won't be talking about belief states, and we won't be talking about POMDP, and we'll be focusing on the observable state case.
Okay.
Yeah.
Okay.
But
yeah, that's a good question.
I think POMDP is it's like still MDP. It's just you have observations, but the transition still follows the MDP. So should that be the evidence?
Yeah, but the issue is that in POMDP, like your policy, you need to make use of the entire history to estimate your state, because so-called belief state, right? So that's something.
Yeah, that's right.
Yeah, that's something that
right.
We're not going to be talking about. But
okay.
I think after you do that, that so-called belief state is a sufficient statistic, and then like it has like very similar properties to MDPs.
Okay.
So that was what I thought, but I have to verify that before giving you the answer.
Okay. Thank you.
Okay, good question. Okay, so here's how we're gonna prove this. So it suffices to consider stationary policies. So let me first quantify what do I mean by this statement. So let's say that there are any policy for any policy pi, there exists a policy pi prime such that pi prime is stationary. And I guess the value function of pi when the initial state when the initial state distribution is mu is the same as that of pi mu prime. Okay, so if this statement is true, we can always construct a stationary policy such that it has exactly the same value as any given policy that's fully general policy. Then we have like reduced our restrict our. Then it says that it suffices to restrict our attention only to the family of stationary policies where nice things happen. Okay, so to prove this, first let's try understanding what this quantity like really look like by applying applying its definition. right? So this is the so S1 sample from this initial state distribution mu, and then all the actions are taken according to policy pi. And then by the definition of this value function, then I'm getting RT minus 1, this gamma T minus 1, R of ST and AT. Okay, so this is by exchanging the order of the summation and the expectation, right? So you need some regularity conditions for that, but let's assume it, and then you can exchange the order, and we can rewrite this as gamma T minus 1, and then the expected value of mu R ST AT. Right, so this is something that we have done just now, right? So now let's further expand this expectation by applying the definition of this expectation. So I guess I'm going to be summing over the individual values that this ST and AT could possibly take. So I'm going to sum over S and A. And then this is a like marginal distribution of this policy, ST equals to S, AT equal to A, multiply with R, ST. Yeah, actually, this is R, S, and A, right? So this is just by the definition of the expectation. And this probability distribution, I'm using this to denote the marginal distribution of ST and AT at step T for this state action pair to be equal to S and A. Okay, now let's exchange the order of the summation again, right? Let's get S A. Let's pull this summation over S and A to the outside. So then we have sum over T from 1 to infinity, gamma T minus 1, and the sum over ST equals to S, AT equal to A, multiply with R, S, and A, and let's group the middle term together. Okay, let's group the middle term together, and then what this means is that this is in some sense the average like frequency of this policy visiting the states SA pairs throughout the entire trajectory, but it is discounted by this gamma. So this is what we call the sum over SA. I'm using this Greek letter nu. Yeah, make sure that this is different from V. This is nu. SA R S A. I'm just giving this whole thing a name called nu, and nu is what we call the so-called occupancy measure. So this is how likely that like over the entire marginalized over the entire trajectory that your state and actions happens to be this SA pair, right? So what we've really just shown is that this V pi of mu, this function is a linear function. It is a linear function of this occupancy and the fixed reward function. Okay, so that's the first component that we want to have, right? And which defines the so-called occupancy measure. Now like we'll construct what this pi prime is. So we'll construct pi prime like for any fixed. Let's fix any pi. We can construct pi prime such that pi prime is equal to pi prime is A given S. So it's a probability distribution of A given S. This is equal to I guess nu pi, this occupancy measure of policy pi, divided by the occupancy measure of policy pi applying only to a particular state. And so if this, yeah. So first of all, what is this? So the occupancy measure. So here the occupancy measure here depends on both state and actions. So the occupancy measure that of depending on only on the state is simply the summation. So it's simply a normalization constant, summation of occupancy measure as a together, right? So this is the individual coordinates. So I'm summing everything up and divide it by its sum, then it gives me a probability distribution. So this is a valid policy, right? And on the other hand, so this pi of like if this is a 0, then I cannot actually I cannot actually do anything, right? In this case, I can arbitrarily set this to be some state independent action distribution. So it doesn't matter like what I take here, what I take this pi 0 to be, right? So it suffices to focus on the first part. So recall why we are doing this. So first of all, verify that this pi prime is stationary. So it depends only on the current S. It doesn't depend on anything in the past, nor the entire trajectory, right? So pi star is from state to a probability distribution defined on the axis. So if we can show that v pi mu is equal to v pi prime mu for all mu, then we're done, right? Then we're done. Okay, so let me move to the next page, and I can how we can move forward with this argument. Okay, so let's first keep track of the two facts that we got. So first of all, this v pi of mu is equal to a linear function of nu, I guess nu pi of mu multiplied with r. So this is this equation. And the second thing is our specification of pi prime as is equal to nu pi sa over nu pi of only s. Okay, so this is how we define how we construct this. So the idea is the following. Let's maybe first yeah, let's like before calculating that, let's calculate what is the transition probability on the pi prime. Okay, let's say we are at state S and we are taking this constructed policy pi prime, and what is the probability that we're going to transition into S prime? Okay, so this is by definition of this is equal to sum of A pi prime A given S and P of S prime S A, right? And if we substitute the definition of pi prime, we get nu S A over nu pi S multiplied with P of S prime given S A. Okay, so we have we now is starting to relate this into pi. Now we can remember that what we're trying to prove. We're trying to prove that v pi nu is equal to v pi prime nu. So let's write let's start from the other side and write what v pi nu is. So again, by definition, this is t from 1 to infinity gamma discounting. Yeah, so this is a definition of this is a definition of the occupancy measure. Right, yeah, because of, first of all, because of this, in order to prove this, it suffices to prove that the occupancy measure is the same, right? So that's why we are proving that the occupancy measure, yeah, the occupancy measure is defined to be this, and then let's proceed. Let's strip out the t equals to 1, because t equals to 1 has only something to do with the state distribution. So this is mu s, and then this is a trick that we're going to be using again and again. So I'm basically taking out the first item from this summation, -1, and then I'm copying everything. Okay, and now let's like take out this gamma, t from 2 to infinity, gamma t minus 2, p mu s t equals to s. Okay, now let's do a change of variable by calling t tilde to be t minus 1. So that the index will be from t tilde from 1 to infinity, and gamma t tilde minus 1 and p mu pi s t tilde plus 1 equals to s. So without loss of generality, I can just replace this t tilde with t again, right? So essentially shift this summation and then changing the corresponding corresponding index. And the next, so we'll try to construct the occupancy metric, specifically construct the occupancy metric with respect to a new to pi prime. Okay, so we'll have t from 1 to infinity. I guess gamma t minus 1, and then I can and then I can again using the tricks that we have, we can rewrite this as a summation of s s prime given a. So what is x prime? S prime is the state that ends up giving us this s prime is the state at the step t tilde that could have given us this s. So it is like moving towards a previous previous time step rather than the current time step. So I can by applying the law of total expectation or law of total probability, I can rewrite this as a p mu pi of s as t equals to s prime a t equals to a, and yeah, capital A, and p of state s prime a. So this is a transition kernel that we are transitioning from this s prime into this x that we observe at t2 time t plus 1, right? So I'm basically expanding this using law of total total expectation. Okay, so once I do that, I can try I've already like created the occupancy measure, because I can exchange the order of the summation of this and that, right? So let me lift this summation over s prime and a prime out. I get that plus and summation of s prime and s prime a, and then the then I get the sum from t to infinity, gamma t minus 1 and p mu and pi and st s prime at equals to a. So this whole thing is the occupancy metric of pi at s prime and a. So instead of s, now we have x prime, but this is the definition of the occupancy metric. So what we can do now is to apply the definition. Like is to what we can do now is to just like notice that to somehow construct the occupancy measure or to construct the transition on the pi prime by dividing this by dividing new pi s and then multiply new s prime at the same time, right? In this way, we can construct the transition on the pi prime, right? So after that, we will let's move to here. So what we're gonna get is mu of s plus gamma and summation only over s prime, and say let's first multiply this. We get nu of pi nu of s prime. Okay, and then we sum over a, right? We will sum over a, then we will have the occupancy metric of pi s prime a over this quantity. So we'll have nu pi of s prime, right? So this gives us the by definition here, pi of a given s, right? So the remaining thing that we didn't write down is s prime given a, right? So this whole thing together give us a state transition on the pi prime as from transition from s prime to s. If we collect everything together, we got a like linear system of equation in terms of nu, right? So what we got is nu of mu pi is equal to nu of s plus gamma sum of s prime nu of pi of s prime, but multiply with the state transition of s prime to s under the constructed policy. Okay, so clearly like the same argument also works like if we replace this pi initially with pi prime, like everything will follow like step by step. So you also have a you also have an equivalent system of equations that is written as in the same way, except that the unknown variable becomes something that becomes the occupancy measure related to nu pi prime rather than nu pi. Oh gosh. Okay, so these two linear system of equations are both these two linear system of equations are like you have a vector pi is equal to let me write it in matrix form so that it becomes clearer. Nu plus, so notice that this summation is simply a matrix vector multiplication. P pi prime multiply with nu, right? So which says that we can calculate this nu by solving the, yeah, I'm missing a gamma. By solving 1 minus gamma p pi prime inverse of the input nu, right? Similarly, we also have that this to be equal to so provided that we can show that this matrix is full rank and invertible, then these equations would show that this occupancy measure of pi and occupancy measure of pi prime, they are identical. Right, these two together implies that these two occupancy measures are identical. Therefore, implies that the value function is also identical between the two policies. So why is this invertible? So notice that P prime is a transition matrix. So it's a probability transition matrix. And so I leave this as an exercise. Show that for all gamma smaller than 1, I minus gamma P pi is invertible. Yeah, once you have this, you plug it into this, you'll end up getting the equivalence. So what I've shown you is that it suffices to consider any stationary policy. For any complicated policies, there always exists a stationary policy such that it has exactly the same value function, right? And this is actually the something that we'll run into again and again. This is coming from the Bellman equation of the so-called occupancy, and then there's a closed form solution that we can solve for this occupancy measure by inverting this linear system of equations. Yeah, so there's a question in the chat. It's an excellent question. Don't you need to show that pi star exists in the first place in order to use this lemma? Yeah, so we haven't gotten to pi star. So far we've only talked about, like, suppose there is a policy pi, we can construct a stationary policy that matches it exactly in terms of the performance metric, right? So I think you're already here. So one corollary of this this proposition is that there always exists an optimal policy that is stationary, right? So now for this, it requires us to I guess construct pi star concretely. So recall, like, what we are defining pi. So we star is equal to max over all policy. So guys, I'm gonna take another 5 minutes. All right. So I hope to end at 2:50. So we star s is equal to we star s is equal to that. So we know so this is optimization over the entire vector. So one question that that concerned us is that whether there exists a single policy that simultaneously achieves the argmax for all these, right? But at least for each fixed s, we can construct the so-called pi. Let's index it by s to be the arg max of v pi s, right? This is something that always exists because this is a scalar, right? So on the, like, as long as we're dealing with I guess, like, just now we've shown that this is a linear function, and the search over pi is essentially the search over pi is essentially the search over the occupancy metric, occupancy measure. And we know that the occupancy measure from the previous slide, it satisfies a set of linear equations, right? So this carves out a particular convex polytope, and the the optimal solution for this always exists, right? Since you have a like non-empty linear, you have a non-empty convex set, and then optimizing over a convex set, a compact and closed convex set, that always gives you a policy that achieves that argmax. But now this is not still not V star, because this is a policy that depends on that has a memory. So we can come up with pi star by choosing always run pi s if s1 is s. right? So this is one way to construct one policy. Like think about this as a meta policy, and this meta policy uses a list of pi s equal to 1 to pi s equal to s cardinality, and you can leverage this, and that gives you another policy. But notice that this policy is not memoryless. It is not stationary because it actually depends on the realized value of the initial state always, right? So then we can apply our proposition to construct a pi prime such that the v pi prime is equal to the v of pi star for all initial state distribution. Therefore, for all initial state 2. Okay, and by the construction, this pi star is fully stationary. It doesn't depend on the initial value. Okay, so I hope that clarifies the question, and yeah, this is also where I'd like to stop here. So I've used a little bit non-typical introduction to Markov decision processes. I didn't get to talk about the Bellman equations, but the Bellman equations are closely related. So like specifically, once we restrict ourselves to stationary policies, then stationary policies satisfy the so-called Bellman equations, and we can rewrite this as an alternative definition of the value function for each policy as this recursive equation. So the left-hand side and right-hand side both it's parameterized by this v pi, right? So I'm gonna be proving this Bellman equations to you at the beginning of the next lecture. And then you can also try it yourself, and it's pretty straightforward using the property that this policy pi is stationary, and using the trick that we've learned to shift this discounting factor by 1 in every iteration using the definition of v pi, right? And we can also like write down the corresponding Bellman equation using the Q function alone, which I leave it as an exercise, and I'll revisit this at the beginning of the next lecture. Sounds good. That's all I'm gonna cover. And thank you all for coming. So if you have been following the derivations up to this point, then great. If not, I'll make the video available. And the scribers should try coming up with a nicely written notes. Yeah, for the derivation of this proposition, I followed the exposition of Chaba at the Simons Institute reinforcement learning bootcamp, and which is a very nice way of viewing the technical subtlety of Markov decision processes, in my opinion. All right, yeah, thank you all for coming. Yeah, please send me emails about or like just post on the Piazza about anything that you'd like to discuss about this course. So the remainder of the course will like not necessarily be like the kind of derivation that we're doing today, but a lot of the components that we'll be teaching is going to be about mathematical analysis, about answering such like questions on the fundamental level. All right. Yeah, thank you very much for coming.
I was hoping that you could maybe explain the occupancy function a little bit more.
Oh, okay.
Yeah, I got lost at that part of the proof.
The occupancy. Wait, occupancy function. Do you understand its definition or?
Yeah, I was hoping you can really explain the definition.
Okay. Okay. So we derived the occupancy from scratch, right? So notice that this is how we like this is the first line is a definition of the value function, right? So think about occupancy about how likely is that you're going to be at this state action pair, right? Because if you are already at the state action pair, then the reward will be the same, right? The expected reward will be the same.
Okay, I guess I'll be more clear. The part that threw me off was like you have two occupancy functions divided by each other.
Oh, I see. The occupancy, the occupancy measure that we defined here on the last but the second line here. So this is a state action occupancy, and state action occupancy measure like is parameterized by state action, and it's about the induced distribution of state action pairs over the entire trajectory of this Markov chain by this policy pi. Okay, and then the state action, the state occupancy is a marginal state distribution induced by this policy pi.
Okay, so
that's why I can just marginalize it by summing up A to.
Okay, yes. So at the right hand side, the equations are pi prime A given I is equal to like those two piecewise functions. The denominator is a trajectory of all possible action.
The denominator, this one?
Yes, this one.
The denominator is a state occupancy.
State occupancy, and the nominator is
it's state action occupancy.
Okay.
Yeah, and the state occupancy is simply the summation of the state action occupancy by marginalize out the action. Right, so it's normalization constant. So we're calculating the conditional probability distribution.
I see. Okay.
Yeah, good question. All right. Yeah, if there are no further questions, I'll stop recording, and then yeah, I'll see you on Wednesday. Bye.
Thank you.